Hey y'all. Today we are talking about properties of real numbers. And up until this point in math, pretty much all you've dealt with is real numbers. Later this year, we'll start talking about something called imaginary numbers, so we will broaden this. But for now, we're still just going to classify numbers that you've seen before. So there are two different categories that we can divide real numbers into. We can divide them into irrational numbers and rational numbers. And these little blue letters that you see above real and irrational and rational, those are just abbreviations that we have, so we don't have to write out the whole word every time. They're kind of fancy letters, right? We can see this I, this R. We call those double struck, so that way we can tell that it's talking about a whole set of numbers, and it's not just acting like a variable. It's not just using the variable R, which might be confused with the radius. And then since we've already used R for real, we have to use a different number for rational. So that's why we end up with this fancy double struck Q, which I know it's kind of weird with the swoopy tail, but typically when you type on the computer, that's what your double struck Q ends up looking like. Okay, so irrational and rational, what's the difference? A rational number is a number that you can write as a fraction. So it doesn't necessarily look like a fraction to begin with. A number like 2, which obviously you can just write as a 2, we could rewrite that as a simple fraction. And when I say simple fraction, I just mean we don't have weird things in that fraction, like maybe a pi or a square root in that fraction. It's just regular counting numbers in the numerator and the denominator. And so the opposite of rational would be irrational, a number that we can't use or can't rewrite as a simple fraction. And those are, you can see some examples over here, numbers like pi and square root of 2. And you'll notice we often use things like pi or this letter E, we'll talk about later this year. But we use symbols for those irrational numbers because they're not nice, pretty numbers that we could represent as a fraction. We need something else to write them more simply. So that's why we use symbols, or sometimes we're just stuck with the square root of 2 and we can't simplify that anymore. So another way to word irrational numbers is they're always going to be a decimal that continues on forever without repeating. And individual numbers may repeat, like you can see the 1 repeats in pi, but the pattern of numbers doesn't repeat. Okay, so within rational numbers, there are more specific classifications that we can use. So 3 different classifications underneath rational numbers are integers, whole numbers, and natural numbers. Again, we've already used a double struck I for irrational, so we use a Z for integers. I think we have the French to blame for that. We use W for whole numbers, that makes sense. We use N for natural numbers, that makes sense. Okay, so natural numbers are your most basic numbers. Those are numbers that are just, I call them your counting numbers. They start with 1 and they just go up. 1, 2, 3, 4, those are all natural. Whole numbers are all of those, but they also include 0. I remember that by thinking whole kind of sounds like the word whole, right? So I'll add that as a little note over here, whole, without the W. And 0 has a big old hole in it. So that's how I remember whole numbers are the ones that have 0. And finally, integers are also those nice counting numbers, but they also include the negatives. And of course, 0 as well. And I think it is important to note 0 is not technically positive or negative. It's a non-negative or non-positive number. Okay, so there's our classification. Hopefully you can see on this Venn diagram, even though whole numbers do include 1, 2, 3, 4, those are already in this circle. If we notice this circle of whole numbers, it wraps around the natural numbers too. So 1, 2, 3, and 4 are included. We just don't have to list them again because they're already inside that circle. Okay, so let's do some practice. Let's name all sets to which these values belong. And it is important that we remember to simplify before we classify these numbers. So we just need to check if these can be simplified first. Okay, so negative 10 obviously cannot be simplified. Negative 10, I like to start in the most specific category possible. So negative 10 would be here in the integer circle. So I'm going to go ahead and classify 10 as an integer using that double struck Z so I don't have to write out the whole word. So integer, that is also in the rational circle. An integer, this could be rewritten as a fraction, right? Negative 10 divided by 1. So it does still count as a rational number. Rational is a Q, not an R. Let's erase that. Okay, my double struck Q for rational. And then all these numbers that we were talking about all belong in this outermost box that says real. I forgot to type the word real here, so I just put this R in the corner. But every single number we're going to talk about in this section will be classified as real, and other things too. Okay, 2.48. This is simplified, it's just a decimal, but I know that all terminating decimals that end, could be rewritten as a fraction. I don't have to know what that is, but I do just need to know that it could be. Okay, so I'm going to go ahead and classify this as, I know that that would be a rational number here. So that's going to get a Q. And all numbers we talk about are going to be real for now. Okay, here's an expression. We can simplify this expression. So pi minus pi is 0. So even though pi is an irrational number, it simplifies to 0, so I'm going to classify 0. 0 is a whole number. So I'm going to get that double struck W. Whole numbers are also in the integer circle, so I have that double struck Z. Those are also rational numbers, and they are real numbers. So we have quite the list going on there for pi minus pi. Okay, D. D is tempting to say, well, it's a fraction, so it must just be in the rational circle. Again, remembering that we simplify first, this does actually simplify all the way down to just 3. And 3 is a natural number. So we have a long list for this one. We have natural. Natural numbers are also whole numbers. They are also integers and rational and real. Alrighty, if you think you have the hang of this, you can try and solve the rest of these yourself. I'm going to start going through a little more quickly, making sure that I simplify first. Here we have a rational and a real. So this one's interesting to note that even though it's a fraction, this is easy for me to classify. I know that this is a rational number and therefore also a real number. If this was given to you in decimal form, this would be a repeating decimal. Okay, so it is a decimal that goes on forever. Decimals that go on forever tend to be irrational numbers. But remember, irrational continue without repeating. All repeating decimals actually can be rewritten as fractions. You don't need to necessarily know how to do that. There is a really cool trick if you want to look it up. But what you need to know is if you see that decimal repeating, it will be classified as a rational number. Okay, so that helps us with G here. I can see that little bar there means that the 5 repeats. So this is going to be 0.15555, which I might not know what that is, but I guarantee it could be rewritten as a fraction. So since it could be rewritten as a fraction, that is a rational and a real. And finally, square root of 7, there is no way to simplify that square root. That is going to be a number that a decimal that continues on forever without any repeating pattern. So irrational, but irrationals are also real numbers. They are not imaginary, which I know we haven't learned about yet, but that is going to come up later this year. Okay, so Gulf Breeze High is sponsoring a charity race. What set of numbers best describes the number of people, P, who participate in the race? Okay, so we have to think about how we would describe the number of people. There could be 0 people who participate in the race. That would make sense. Be sad, but it would make sense. We could have 75 people compete in the race. We could have 1 million people competing in the race. We need to think about what type of numbers all of those belong to. Okay, so they are all, I'm going to skip natural for now. They are all integers, but integers also include negatives. So I'm going to say, while they are included as integers, that's not really the best set for me to say that these numbers belong to, because the number of people participating will never be negative. Okay, that also goes with rational numbers. So rational numbers are going to include fractions like 1/2 or 1 7/9. Okay, so again, while 75 and 1 million they do belong to rational numbers, all rational numbers don't necessarily best describe, and that's our key word there, best describe who's participating. Irrational, definitely not. You're never going to have 3.1415926 something. That just is never going to make sense. So it's definitely not irrational, and that leaves, it's really just the natural numbers that best describes. Okay? I'm going to clarify that with, we did include 0. 0 is not a natural number, but of my options here, that one's the best option. So I would maybe pick whole numbers, but since this is multiple choice, natural numbers is going to be the way to go. Okay, the solution to the equation is what type of the numbers listed below. Circle all that apply. Okay, well, this kind of goes back to example 1. We need to simplify before we classify. So let's go ahead and copy that down. 3D plus 17 equals 13. Let's do some inverse operations to isolate D. So instead of adding 17, we'll take away 17 from both sides. This leaves this equation equivalent, but we're working on isolating that D. To get rid of that 3 times D, we can divide both sides by 3. 3 divided by 3 is just 1, but instead of writing 1D, we don't really have to write that 1. We know that 1D is just the same as D. We've isolated the D, and we end up with -4/3 as my solution. So if that's my solution, let's go ahead and classify that. -4/3 is a rational number, so let's circle that guy. Well, it can't be both irrational and irrational, so it's definitely not number 2. It is definitely not positive. It is indeed negative, -4/3. And even though integers do include negative numbers, remember it's your negative counting numbers are integers. It would have to be a number like just plain -4 or -3 for it to be classified as an integer. So just rational and negative. It is also real, but that's just not an option that we have. Okay, moving on. A set of numbers is closed or has closure if the operation on any 2 numbers from that set is also a number that belongs to that set. That is a whole lot of words. What the heck does that mean? So the question you want to ask yourself on problems that ask, because these show up on SAT and ACT, really just ACT actually, but you want to ask yourself, is the answer still part of this same set? And if your answer is yes, then we say that that set is closed. So let's look at an example. The set of real numbers is closed under addition, which means I should be able to pick any 2 real numbers. Let's pick 2 easy ones. Let's do 2 + 3. 2 is a real number, and 3 is a real number, so we have to pick two numbers that both belong to the set in question. It's asking, is it closed under addition, so I use addition in the middle. And then my question is that answer, every single time, will that answer be a real number? Okay, and clearly in this case, yes, 5 is a real number. So yes, I came up with an example that shows that this is true. Can we think of an example that would make this not true? So let's start to pick weirder numbers. Maybe I can pick a rational number and a natural number. -4/3 plus 3. Okay? Well, -4/3 is rational, which is also real. 3, we already said is real. So that's going to be, what, 5/3, I think? 5/3 is a rational number, and rational numbers are real numbers. So again, since this is a real number, it's looking like this is true. Okay, let's pick other numbers. Let's pick like pi plus, maybe I can do a fraction, pi plus 1/2. Okay, I might have to use my calculator for this. This is going to be 3.64159. Okay, so it's not exactly pi, right? It added a half there. But this is still going to be a number that continues on forever, or I'm sorry, a decimal that continues on forever without repeating. So this does still count as an irrational number, right? So this is an irrational number, and all irrational numbers are still real numbers. So I don't think I can come up with any examples of two real numbers being added that would ever not be a real number. My answer's never going to be an imaginary number because I just don't know what an imaginary number is yet. How do I get an imaginary? So because the answer is yes, because my answer to this is always part of the same set, they're still real numbers, I'm going to say the real set of real numbers is closed under addition. Yes. Okay, the same, I'm not going to go through all that work, but the same is going to be true for subtraction. No matter what I subtract, I could do pi, I'll do one example. I could do pi minus 3, right? Two real numbers, I used subtraction in the middle. Is my answer always still going to be a real number? And in this case, it's 0.14159. So that is still irrational. Irrationals are real numbers. So again, I'm never going to be able to find a counter example, and that's an important word. I will never be able to find a counter example where the answer is not real. So yes, the set of real numbers is closed under subtraction as well as addition. Okay, so let's do some more examples then. Determine if each statement is true. Integers are closed under multiplication. So I need to not just prove that this is true, right? Okay, so I could do like 5 times 3 is 15. Both of these are integers. My answer is still an integer. So it's looking good. Can I think of something that would make this not true? So even if I use like -6 times 0. 0 is always a good one to look at. -6 times 0 equals 0. 0 is still an integer. So it looks like this is closed. Integers are closed under multiplication. That is a true statement because I cannot think of a counterexample. Irrational numbers are closed under subtraction. Okay, so I need to pick two irrational numbers. I am not allowed to. I'm going to write this in red because this is wrong. I cannot use pi minus 3 as my counterexample because pi is an irrational number, but 3 is a rational number. So that is not a good example because I'm only allowed to use irrational numbers for that left side of the equation. Okay, but tricky enough, I can do pi minus pi. So this is an irrational number. This is an irrational number. And remember, my question is, when I subtract those, is the answer still an irrational number? And pi minus pi is 0, but 0 is not an irrational number. It is, in fact, a rational number. It's a whole number, most specifically. But because this answer does not belong to the original set, this is false. There is not closure for irrational numbers under subtraction. Okay, whole numbers are closed under division. Again, we can think of things that make this true. 6 divided by 3. We have a whole number divided by a whole number. And my answer is a whole number. So it looks closed. But we don't need to prove this true all the time. We're just looking for one example that might prove this false. So what if I flip-flop those numbers? Instead of 6 divided by 3, what if I did 3 divided by 6? 3 divided by 6 simplifies to 1/2, but 1/2 is not a whole number. 1/2 is it's a rational number. So, and it's a rational number that is not whole. Okay? So we are going to say that whole numbers are not closed under division. That is a false statement. Okay, odd numbers are closed under addition, so I can pick any two odd numbers. 3 plus 7. 3 plus 7 is in fact not odd. My answer there is even. So that was pretty easy to prove false. In fact, any two odd numbers will be even. Alrighty, determine if the set is closed. So pretty much same as example 5, but now it's just not true, false. We're saying, does a set have closure or not? And if not, we have to give a counterexample. So maybe try these on your own, or you're welcome to follow along with me. So rational numbers being closed under division. This actually is something we are going to talk about later. So I'm going to skip this guy for now. I probably shouldn't have included this as an example. Okay, let's move on. Multiples of 5 under multiplication. Okay, so if I think of any two multiples of 5, maybe 5 times 25, it's going to be 125. Okay, that's looking like it's closed. Maybe 10 times 10 is 100. Yep, it looks like all of my answers, no matter what I do, if I multiply 2 multiples of 5, my answer will still be a multiple of 5, so this is going to be closed. Okay, whole numbers under subtraction. Okay, so I can think of things that would make this true, but can I think of one that wouldn't? Maybe if I take away a bigger number from a smaller number, if I do like 2 minus 7 is -5, and -5 is an integer, but not an integer that's a whole number. So it looks like this is not closed, or we can also say open. Most of the time on ACT, though, you're going to see them say not closed, or it does not have closure. But you can say open, it's faster. Okay, even integers under addition. So if I add an even number and an even number, there is just no way that's going to be odd, right? And actually, we talked earlier, we said that 0 is not positive and it's not negative, but 0 does technically count as an even number, interestingly. So even if we ended up with 0 under addition, like 2 plus -2, right? Because even integers we can use negative equals 0. 0 is, and you can Google it if you don't believe me, an even number. So I can't think of any time it would ever be odd. So this is closed. Okay, complete the table below showing which sets are closed under each operation. So adding integers will always be an integer. I cannot think of a single counter example for addition or subtraction. Multiplying, negative times a negative is positive, but if I'm multiplying those counting numbers, it's always still going to be a counting number. So this one's closed. Division's a different story though, right? So division with integers, we could do something like -1/2 divided by -2. And integers could be positive or negative, but they cannot be fractions, right? So that simplifies to 1/2. I'm going to go ahead and put open, shorter word to write. So not closed. Integers are not closed under division. Okay, rational numbers. Again, rational numbers, adding two fractions. Maybe a whole number, but whole numbers are still able to be rewritten as fractions. So we are going to be closed pretty much under all operations. And here's that exception that we skipped earlier. So let's talk about that now as our last little thing in these notes. Okay, if you Google are rational numbers closed under division, you kind of get conflicting answers. Technically, no, it is not closed. It's open because of the one case of when we divide by 0. So let's look at that up at example 6a. If I divide by 0, 7 divided by 0, 7 is a rational number, 0 is a rational number. The interesting thing is, and the reason that typically we do still say that rational numbers are closed under division, is because there really isn't even an answer to this problem. You end up in a calculator, it'll tell you have an error. Typically in math, we say that this value is undefined. And an undefined solution doesn't belong to any set, right? So since you don't even get an answer to this problem, it's almost like it's an example that you can't really use in the first place. So you will get some people that say rational numbers are, and it's not just some people, it is mathematicians. They will say that rational numbers are functionally closed or contingently closed under division. Knowing that, yes, there is this special case where when I divide by 0, we just don't even get an answer. Which again, some mathematicians say, well, since I can't do that, divide a rational number by 0, which is a rational number, then it's not closed. So this is not a problem you're ever going to see on a quiz or test. It will not show up on ACT, but it is just something that's interesting to think about, that there are some things even in math that even the best mathematicians don't always agree on. So on that note, have fun with your homework